And this title is actually the title of a draft that we're working on now, and hopefully will be submitted within like the next week or so once doctors are go ahead. But because we're a little bit, you know, I'm trying to get as much of the main point across to you, I have a subtitle which is one of the main conclusions of the work. And what I want to figure out, or what I want to try to convince you of today is my answer to this question, which is, can a distributed interference network do better than TDMA? And to kind of explain what I mean by that, I'm just going to gloss over some of the terms that we're all sort of familiar with. I'm a wireless guy. I like wireless networks. And I think everyone kind of understands the point that when we have multiple flows of information happening between different sender-receiver pairs, because we have this wireless medium and it's shared, we have issues with this phenomenon of broadcast repositioning. So whenever we have two or more flows of information trying to convey messages to each other, we have this interference problem where our need to get information across to our receiver hurts someone else's transmission. And so this has been studied a lot throughout the years in the form of an interference channel, theoretically. And I just want to highlight what some of the approaches have been in the past to deal with interference and compare like how they perform in different regimes. So one approach that we've been using since the beginning of communications and understanding what signals really are and how they can be represented is orthogonalizing. So if we have two users sharing a medium, can we split up their transmission so that they don't experience interference at all? Frequency division, time division, things like that. The reason why it performs okay in pretty much every interference regime is that we've removed that interference, right? But in order to do that, we usually have to reduce bandwidth. Treating interference as noise, it's exactly as it sounds. Basically, we just have higher interference noise floor now that there's another signal there. Obviously, it should perform very well when that interference power is in your own receiver noise floor. But when that power is very high, we suffer a huge cost in terms of reduction rate. And two approaches that came about through the years of looking specifically at the interference channel are this idea of using multi-user decoding, or trying to, at a receiver, decode multiple parts of a message. In multiple access, the goal, the idea was that you had to decode both users' messages or all the different interference messages. The reason why it doesn't work in a very weak interference regime is that you have to decode the other user's message despite the fact that you don't really want to know it, which led to the concept behind, or the main concept behind the Kobayashi set of techniques, which is that every user has a common message that's supposed to be decoded by everyone, and a private message that, you know, can kind of reside as noise. If we look in practice, almost every network in wireless uses these two approaches, which are the two that we've known since we first started doing, you know, wireless transmission. And the rationale I have for that is that the amount of information you need at each node in order to do these two, it's fairly constant in the size of the network. It doesn't grow as the complexity of the network grows. For instance, for doing TDMA, each node really only needs to know when to start transmitting and when to stop, right? On the other hand, these other two techniques, because you need to be able to either separate different streams or know what sort of channel they're coming through in order to decode, you have to know all the different channel gains, which grows as quadratic with the number of interferers. So the key challenge from my point of view of looking at a lot of these distributed networks, that have different flows interfering with each other, is that nodes don't know what the entire network looks like, right? And that's what really makes it distributed. If they all knew what the network was, they could use that knowledge to kind of synchronize what they're going to do. So to kind of formalize that idea even more, we have this concept which we refer to as a local view, and it's actually a really simple idea. So if you have some set of parameters that describe your network, in this case it's just a two-user interference channel, so there's 2 senders, 2 receivers, and 4 channel gains that describe the entire channel. What a local view means is that you only have, say that I am this Android phone. My Android phone only has knowledge of part of those set of parameters. In this case, it only knows its direct link. And each setup of a particular local view, for instance, if I only knew these 2 channel gains, describes what some network architecture gives you. So if, for instance, my phone tried to compute or estimate these channel gains based on some sort of passive measurement of beacons from base stations, I would have this knowledge. Whereas if, say, the base station measures, channels from training and then lets me know what my interferer is giving me, we might have this case. For this particular network, there's really 7 different local views to look at from the point of view of one of these phones. And there's also the case of having full knowledge, right? This particular case has been studied in great detail for the last 30, 40 years, longer than I've been around. But my focus today is going to be on these, and in particular because there's multiple users in this network. Each of them have their own view of what the network looks like. I'm going to assume that the view of the other user is the mirror image of mine. So if I know my direct link and outgoing interference, then Eric, who is the other user in the network, knows his direct link and his outgoing interference. And neither of us knows the entire network. The one key point I want to kind of drive home is that this isn't a model of noisy estimates. It's a model of whether or not you have information. So I'm assuming that the information you have is perfect. There's no concept of error, but the ones you don't have could be anything.
So you're just going to focus on the 50% knowledge?
I'm actually going to look at, in the paper we look at all of these cases. I'm going to key in on one of the main conclusions about all of these, because we find the capacity region for all of these with some constraint, and compare the performance that you noticed.
So can you repeat the rest of the explanation on the how? So you are assuming errors for the estimation, right?
No errors.
No errors. Perfect estimation.
Right. So if for instance, like this example here, then I would know I'm assuming that you have your channel gain to your receiver perfectly, and you have your channel gain to your unintended destination perfectly, but those other 2 gains could be anything within the support of channel gains.
So whether it's perfect estimation or just absolute normal.
Right. And this is the kind of model, we're not building a system from scratch maybe, and there's a network architecture already in place, and this is all that it can give you. These are the only channel gains that it's measuring.
But I'm thinking, but that's not the general cases in most wireless communications. For most generally, they have some knowledge, like full knowledge on the channel gains, but some errors in the estimation. That's the most general situation.
Right, and one thing that we can do going forward from this is not necessarily looking at noisy estimates, but looking at different levels of granularity in terms of what you know. So instead of saying when I don't know a channel completely, it could be like 1 to infinity or something like that in terms of SNR. Let's say I know it's in some range, right? It's 0 dB to 10 dB or something like that. And that's the next step that we're going to be looking at. But just for today, I'm going to look at these cases where you have maybe no information. Yes?
These blue arrows, they represent the channel gains that you know exactly. There's no error.
Right. And I'm going to use these diagrams again, so I should probably make this really clear. The blue represents what the top direct link knows, what the transmitter of the top guy knows. So blue is always going to correspond to the Android phone, and red is going to be the view of the iPhone.
What I just want to make sure is these blue link gains, you know exactly, right?
Right.
And these dashed, these dotted arrows
are the ones that are
you have no absolute knowledge. But that means you know them. You know that these channel gains will conform to some kind of distribution, or
Not the distribution, you know the support. So it's more similar to
You know the range.
right, exactly. It's similar a little bit to the idea of a compound channel, except that instead of one uncertainty set, there are multiple uncertainty sets, and those uncertainty sets are different at each person making some decision about
Is it one of the
transmission.
assumptions that within this range, that the unknown channel gains are uniformly distributed?
No, there's no distribution. So
It's just unknown. within
right,
the-
right, and you have to satisfy all the possibilities of what it could be. As I mentioned, I'm only going to talk about symmetric cases today. So Derek's local view is going to be the mirror image of my own. So far there is an actual channel state, a realization of the channel, and from that we have this local view with, you guys have just asked, perfect information on some of the links and complete non-information on the others. What I'm going to say that each transmitter does with this is that, okay, I have this idea of what the channel looks like and what the interaction between me and the other user is. From that, I'm going to have some sort of response. And that response is a mapping of, I see these gains, I'm going to use this transmission technique. Mathematically, some encoding function, and that encoding function also has some codebook with the rate. That rate depends on my view. The other thing I'm going to assume is that this function is globally known. So it's this idea of to model a protocol, for instance. In some other sense, if I knew what the other user saw, I knew how he would react to his local view. The reason for that, one, is to kind of couple the uncertainty in the system. You have the uncertainty of not knowing the entire channel state, and you also have this uncertainty of not knowing what the other user may do. And this just makes the problem a little bit easier to kind of get a grip of. The other reason is this is kind of an abstraction of how a lot of protocols work. All of them, even some of the ones that do some sort of stochastic multiplexing, are dependent on a concept of state. 802.11 with its backoff, that contention window varies with what's happened in the past. So in the little subtitle I had in the beginning, I wanted to ask if these policies could do better than, these policies that depended on incomplete knowledge about the network could do better than TDMA. And the reason for that is, we always, or in many systems, we use some sort of orthogonalization scheme like TDMA. And we also need some concept of what is a minimum level of performance we get across all states. So, as I mentioned, a lot of things use TDMA. In truth, even with local information, even with an incomplete view of the network, you can always hedge your bets for a specific channel state. The problem with that is that in order to do so, you may have to, in a lot of other channel states, say, okay, I'm going to be completely silent. Just for this specific channel, whenever I see it, I'm going to get the full capacity region, but all the other ones will just get 0 rate. And that's a little bit unsatisfying. So what I'm going to say is that for any channel gain, the rate points that you get with the policy that you use has to at least be on the boundary of the TDMA region or better. And that means that we can't sacrifice too much the performance in another channel state in order to get more rate in another. So the paper has a lot of things that it talks about. The big one, at least from the point of, we're sending to IT transactions. So the big thing that we kind of key in on there is capacity regions, of course. But one of the main conclusions is that a lot of the local views don't give you enough information to do better than TDMA. Provably don't give you enough information. And so that answers how much knowledge nodes need to know in order to do better, and also what knowledge, which I'm going to key in on in a second. So in particular, of the symmetric view setups, these cases here all can't do better than TDMA. And one that is really kind of surprising is this one, right? Because you have almost full knowledge of what the channel looks like at each user. What you don't have is the amount of interference you're incurring at the other receiver. And when you think about how, if you're familiar with the Hankobayashi technique, what the Hankobayashi technique uses is knowledge of that particular link to determine how you split your message into a private component and a common component. On the other hand, these cases can do better than TDMA if the channel state allows. Which one is better out of 1 and 2? Neither one completely does better than the other one. There are specific cases, for instance, if one has a considerably higher SNR than the other, where one may do better than 2.
Why 1 and 3 are different?
So in 1, you have knowledge of your outgoing interference. So if this is from my point of view in this corner, I would know this in 1, but I don't know it in 3. In 3, I know my interference noise floor.
From the system point of view, it's same, because it's just one. If you
From
the system point of view, considering the both regions. 1 and 3 look same.
Oh, but that's the point, right? That there's 2 users here, and each of them sees something different. So this knowledge, because in 1 we can do better than TDMA, this knowledge of this link is more valuable to this user rather than the other one. And to kind of show why that's the case, I'm going to actually focus on 2 and 3 to show why in some cases you can do better than TDMA. In order to do so, I need to actually have a channel model to talk about. And we study this mainly for the Gaussian channel, but the way we build up to that is by using this idea of a linear deterministic channel, which actually came out of David Say's group. The key benefit of that is that it gives kind of a nice cartoon depiction of the Gaussian channel that has a lot of intuition. And I'm going to just explain that really quickly, and the idea behind it. So if we have a wireless transmission, this transmitter sends electromagnetic waveform, and at the receiver we have some output waveform, right? And it has power characteristics, it has an amplitude, things like that. At the same time, we have a noise waveform, or some noise samples, and that also has some power and amplitude, things that basically convey the idea of how loud it is. Similarly, we have an interference signal, which is the red guy, and that has some power. Now, if we look at this in terms of comparing their relative powers in dB, if the power of one signal is much larger than another, intuitively, if you take like a sine wave and it has a really high amplitude and you have a little bit of noise, you can still kind of get the idea that it's a sine wave, right? So the large-scale variations are still easy to see in a signal. So you can kind of separate the signals into different levels of resolvability. The terminology used here is a little bit more towards the networking community, in that there are some parts of the signal that you can capture even above an interference noise floor. There's parts of the signal where if there's information in here, basically you have information bits colliding, and the part of the signal that's at the noise floor is very difficult to reliably decode. So what I'm going to call those are irrecoverable bits. If you transmit at that level, then there are some bits there. It's just you can't decode them at the receiver, right? So in this particular example, we had say, our waveform could be represented as some sort of binary representation in 5 bits. These top 5 are easy to get even though there's an interference signal, and this other one we may be able to get depending on the structure or the rate of the interference. So that has kind of this representation. We have 5 binary inputs and 5 binary outputs for this top link, and 1 binary input here coming from our interferer. And because this doesn't really describe the entire scenario, right? We have transmission in the other direction. We get this representing an interference channel. And I want to just mention that we always have the most significant bits at the input or the set of most significant bits at the input aligned with the least significant at the output. And the idea behind that is that your most significant ones are the ones that get through above that noise floor. So I said I was going to compare the view 2 and view 3 because one did better than TDMA and one didn't. And just to remind everyone, the information not known in view 2 was the direct link of the other user. So in both of these, I'm assuming that I'm taking this from the point of view of user A. In view 3, what you didn't know was your link from your transmitter to the other receiver. And to do better than TDMA in view 2, first we need to look at, okay, I know that this top bit up here causes interference with something at receiver B. I don't know exactly where in the signal it aligns, but I know it may interfere with something. At the same time, I know that this here is at the same level as some component of the signal of user B. I don't know that it will or won't interfere completely because I don't know exactly what the other guy's going to be doing, but there's a possibility of it being interfered with.
So when you say better, or when you compare it to TDMA, are you looking at sort of the rate region?
Yes.
If
Or
you with TDMA, as
if
opposed to
a
rate?
particular rate point can be achieved in one channel state while still achieving at least some point on the boundary of TDMA in all the others. So it is a region that can be constructed from that.
But it depends on sort of because you're sort of doing this for every value of channel state. There is something that you don't know here, right?
Mm-hmm.
So are you sort of looking at the rates that you can achieve for each of these users across all these possible sort of...
All the possible channel states that are consistent with the two feeds. So for instance, if you think in terms of, there's 4 parameters, and I know 3 of them, so that's I know what subspace of the full channel set of channel parameters could be. Similarly, the other guy knows some subspace, and in that intersection lies the real one. But for those entire individual local views, I only have one response. So if another channel state had occurred that was consistent with either one of them being different, we still do as good as TDMA in that other channel state. So one thing that kind of comes out of this too is that when you have some information that's common between the two, so in this case they would both know the crosslinks, right? That makes the problem a little bit easier to look at because there's some information that's synchronizing their knowledge of the network and of what the other user may possibly be doing. But getting back to this example.
And so what is the encoding strategy here?
In this particular one?
Yeah.
So in the end, what it turns out to, for the layered or deterministic model, you can think of each layer being either shared as TDMA or some sort of a orthogonalization-based scheme. What happens though is that, for instance, in this case, because we know that these are neither interfering or being interfered with, we can use those for free. So it still separates into this kind of idea of splitting a signal into different layers of resolvability. There's the high or a large power component that sits at the same level as our interference signal, and a component that sits at the noise floor. That's one of the nice things about this particular model, that there's an analogous scheme for every representation of the different layers in the form of some sort of layered code. So in this case, we could do better than TDMA because we had some bits we knew we could get for free. There was an opportunity there, and because of that, we can use that while still doing some sort of orthogonalization on the contested bits. In this one, the crosslink could have been anything, right? So from the point of view of our inputs, how do we choose what inputs to send? we see that, okay, if this link was 1, then we have this constraint on our most significant bit. It can't interfere too much with the other user's transmission. If it was 2, then it's the top 2. And so on as we sweep the range of possible channel gains that it could have been, we get always a pair of our input levels that are constrained in some way. It's always a pair because we know that direct links of the other user. So it's true that some of our signal may be above his signal and easily decoded and removed, but because we don't know which parts of our signal are there, we can't use that freely. We don't have that opportunity. And because of that, there's a lot of algebra that takes all those bounds and puts them together in a pretty way. But the main point at the end is that you can't do better than TD-main for this specific view. And the outer bound means exactly, at least for the deterministic channel, the rate region you could get with TD-main. So this is the deterministic channel detection of it. It's simplified in the sense that we're only looking at binary levels of things. But the extension to the Gaussian channel, if you're familiar with the set of papers, there's a lot of within a constant gap extension from this channel to the Gaussian one, and we do the same. It requires a little bit of tweaking on making a genie that gives you just the right amount of information that you aren't loose in terms of that bound. But one thing that is a little bit different, it's not that you can't do better than TDMA at all, it's that your gains from, say, more efficient power management or something like that are bounded, regardless of the SNR of the channel. So even if you're at high SNR, even if noise is not really the limiting factor in your network, you can only get maybe 1 or 2 bits better than doing some sort of TDMA scheme. The other thing, this is actually a really basic concept, is that in those views where you couldn't do better than TDMA for a 2-user, if you extended those same sorts of views, so for instance, if I didn't know that my outgoing interference link to Gareth, and I added Dr. Mandayam to the network, and I didn't know my outgoing interference to him as well, then in that case as well, I can't do better than TDMA. So for larger networks, the negative kind of disappointing results still hold. What we don't know about the other cases is the benefit to cost ratio of, now I need to know more channel gains, but I'm still going to be more constrained because there are other interferers that I have to kind of acquiesce to. So there may be this issue of diminishing returns as the scale of the network grows.
So in your comparisons, did you account for the fact that it cost you something to get the channel information?
No, not at all.
Therefore, it might actually make it worse, right? CDMA will look even better, right?
Yeah.
Right or wrong? Because we look at overheads.
The way that we set it up is to kind of abstract away any optimization of any adaptive training scheme. Basically, you have some training that already occurs as part of the protocol already, and you get that and see what you can get. But yeah, if you factor in the cost.
Yeah.
So to kind of wrap up the main theme of one of the conclusions that we found in the work, can a distributed network do better than TDMA? And this gets back to your question just now. How distributed do you mean by distributed? If you have to learn 3 out of 4 channels, and it costs a lot to learn those channels, then is it worth it? So on kind of a different tangent bit of work that we're looking at now, if you don't want to spend a lot of costs looking at learning large components of the network, can you do something else to get better than TDMA performance? One of these ideas is cooperative modes, either at a transmitter or at the mobiles or at the base station. But in those cases, yes, you may do better than TDMA, but are those also distributed networks now? I mean, how much does it cost to actually do those newer techniques? And those are the 2 areas that I'm focusing on now for the rest of my work. I'd love comments on either of these, your ideas. And yeah, any questions or comments?
Roy? All right, so maybe you'll get a chance to talk to some of these guys.
Sure.
Okay, thanks, Ed.
Thank you.
Okay, so next up we have Gavin, who's going to be the second part of this double header.
The second part of the doubleheader, yeah. So I am, as Dr. Madai mentioned, his academic brother. We were both advised by Benamage in Rice. And what I'm going to be talking about today is kind of a very high-level look at the work that I did for most of my PhD. And I'm going to leave all the details under the rug and really talk through what I've done by way of example. And it's going to look at the same kind of question that David addressed in the four-terminal network, is when is it better to do scheduling and say, all right, I have access to the channel, I can broadcast as loudly as I can to my intended receiver and get a high rate. And when is it better to share the medium? Do some kind of power control where we all talk a little more softly, but because we don't interfere too much, we can all use the medium at the same time. And this is what we've been looking at for my work. So I don't need to go through this example very much since David just spent his talk describing it. But there are two ways that you can get information for these two flows through this network from A to B and from X to Y. The first one is in time slot 1, terminal A transmits. Y doesn't care what it receives because in time slot 2, terminal X transmits the data intended for Y, and terminal B ignores. The alternative, so this is the shouting case. This is each terminal uses maximum power to transmit as much as it can in a time slot. The alternative is that each of those A and X turn down their power and we share the medium. So in time slot 1 and 2, both links are active, but somehow we're using some scheme such that we can cancel the interference from the other user. I didn't care too much about how that works, although that is a big problem. The key here is that things are interfering. Our packets are interfering. They're not colliding. We're not going to think of this from the networking layer perspective where two transmissions that interfere are both lost. We're going to say that no, we can't actually resolve what we're looking for. So in determining which of these two schemes to use, the total time orthogonalization or this interference mode, we have to look at what is the optimization criteria. What is it that we're trying to optimize? If it's complexity, if we want to have a very low complexity system that's very easy to implement, the answer is going to be do TDMA everywhere because it's very easy, as David said, it's an order N, or order 1 really, channel knowledge required. But if we're looking to maximize performance, and we have opportunities where we can exploit channels such that we can allow synchronous or simultaneous communication, then we can do better. We can get better performance. So if we're looking for that higher performance, we need some methodology to do network management. The issue, though, is that it's the topology, it's the channels between these links that determine which scheme wins. If these links are really closely packed, then TDMA is going to be the right answer. And we just heard about if you don't know enough information about the network, then TDMA is going to be the right answer. But assuming that we have a lot of network knowledge, we're going to make that assumption that we know everything about our network. Can we derive a general framework for determining when to do TDMA and when to do shared or interfering transmissions? We're going to look at this in the larger network. We're going to move up from what David just described into a network with many, many, many terminals. And this is a cartoon depiction of it. We're going to assume, first of all, that we have synchronized time slots. So where I said before, time slot 1, time slot 2. All of these ad hoc nodes have some kind of a GPS clock, say, that allows them to all be synchronized. Getting away from that assumption is something that we've looked at, but it turns out to be quite hard. We're going to assume also that they're half duplex, so you either transmit or receive, but not both at the same time. And everybody is sharing a common bandwidth. So these are classic ad hoc network assumptions. The one that I want to point out, though, is that we have this variable link quality here. And I'm going to measure or describe the rate that the link can support using a path loss dominant channel model. So if these two terminals are very close to one another down here, they can support a much higher rate between them in one time slot, say, than from this terminal to someone clear across the network. So we're using this geographical notion for our ad hoc network. And within this context, what we want to look at are trying to solve the scheduling problem. If we have information flows needed across this network, we need to do the scheduling, we need to do the routing, and we need to do the power allocation all jointly. So what might that look like? Well, suppose we have two sources in our network. These are sources for two different information flows, the blue flow and the red flow. And they're indicated as sources because they're all colored and they have a lot of bits to transmit. Their sinks are the open circles. Throughout this talk, I'm going to use sources are solid and sinks are open. Sinks somewhere across the network. So the question is, can we determine the schedule, the route, and the power allocation to get data from the source to the sink? For the blue flow, it might look something like this, where we hop from here to here to here to here, and then for the red flow, something like this, down and across. The question is, which of these links can be active at the same time? And how do we manage this area here where we have information that's kind of crossing the same geographical area of the network? So there's going to be interference. How do we manage that? And so this is the problem that we're looking at. The analytical complexity of this is huge. I'm not going to go into the mathematics. All I want to point out here is that we're trying to maximize the minimum throughput. That's our objective. If we let eta be the throughput variable and f indexes our flows, we want to play with the schedule and routes held in this indicator variable and the power, such that we maximize the minimum throughput. And this is subject to some huge host of constraints that all get written out. Don't worry about what they are. The key is that we're looking for constraints such that we have half duplex terminals, continuity of route. So if I transmit a packet to David, he has to be the next transmitter. Packets can't disappear and reappear in other parts of the network. We also don't allow broadcast. So we're assuming simple terminals. I transmit a packet to only one receiver at a time, and we don't allow medium access. So I'm not going to receive more than one packet at a time. Now, if we have an SINR constraint, and we say that a packet is considered to be received if the SINR is above some minimum threshold, then we can take this program and do some rewriting of it to get a linear program that you can solve using column generation techniques or something like that. But we're going to drop that constraint and say that we just consider no SINR constraint. The rate is determined between two users strictly as a function of distance between them and the other interference in the network. This leads to a nonlinear, non-convex problem. What it also means is that the size of a frame, when I transmit a frame to David, for instance, if he's close, that frame can accommodate more bits than if I transmit to someone sitting on the other side of the room. So when we talk about packets, generally we talk about a packet having some predefined number of bytes, say 1500 bytes is a common packet size. In our model, we're moving away from that, and we're saying that our frames can be variable size. So that's a knob in our system that we can change. Is it might make sense to transmit more smaller frames than one larger frame that meets some SINR constraint. So that's something to keep in mind. When I talk about a frame or a packet, it's not a packet of some specific size. That would be the case if we had an SINR constraint, but we're moving away from that in this model. And as I said before, the rate on the link is specified using this log 1 plus SINR. So how do we solve this? This is a very complicated mixed integer program that's actually NP hard. So you would have to search through every possible combination of schedules and routes. And for each one, you'd have to look at every possible power allocation for the active transmitters in each time slot because it's non-convex. So what are we going to do to get an efficient solution? We're going to propose a decomposition technique. We're going to say, let's look at this problem in pieces. So here I have a little picture, it's another cartoon, of three flows, red, blue, and green. And we want to study how the frames and the flows interact with each other. And interact is kind of a keyword because that's what they do. When they come close to each other geographically and in time, they start to affect one another. We want to look at how they interact in both space and in time. In particular, we want to find an efficient solution to this problem, not searching the whole solution space. And to do so, we're going to decompose by frames. And for each frame, we're going to compute a schedule, a route, and a power allocation. What I mean by that is that we're going to look at one frame for one flow at a time and consider that to be a subproblem. So in this case, we're going to say, okay, let's study a frame coming out of the red source. Let's allocate resources for that frame. Then allocate resources for the blue frame, and then the green frame. Now, one thing I should mention is that we're assuming for now a Poisson distribution of our terminals, two-dimensional Poisson, which is basically uniform across the space. And what that means is that the flow that has the furthest distance to cross, so in this case it's the red frame, is the one that is statistically most likely to experience the longest hop between two terminals, which means it's the one that's going to have the tightest bottleneck and should be allocated resources first. So that's the frame that we're going to consider first in our allocation. In this case, that's the red frame. So you say, okay, here's the red flow. We want to get data from here to here. How do we do that for one piece of information? Well, perhaps the solution looks something like this. It's a 3-hop path from the source, here, here, here. Now, given that these resources have been consumed by that red frame, what is left over for the blue frame? We subtract these resources away and we say, all right, what can we do with what's left over? Maybe it looks something like this. So now the blue frame is the second subproblem that we solve. So we've solved one, now we've solved two. Removing those resources from the network, what do we do for the green frame? Well, maybe it looks something like this. So this is a picture of the routes that come out. I haven't talked about the power allocation or the schedule yet. But you can see in this case that There's a little bit of a crossing here where terminals have to, the frames have to time synchronize to get through that half duplex terminal. Yes?
What does frame mean here? Is packet?
So it's a packet, yeah. I use the word frame to try to get away from that notion of a predefined packet size. But a frame, you could think of it in a lot of ways. You could think of it as a collection of very small packets, the number of which is dictated by channel conditions. Each packet is just a couple of bytes. You can transmit some number of them in a time slot at some rate. But yeah, it's essentially a packet.
So your allocation unit is cannot is for one frame or one flow.
Yeah, one frame for one flow. So in this case, we allocated this frame first for one flow. Now, what we will look at in a few slides is when we have more than one frame that we want to allocate. So we want to do some streaming, in case of maybe streaming data flow, like a video stream, for instance. Then we allocate 2 frames, 3 frames, 4 frames, and so on. Still in this method, one frame at a time, because that gives us polynomial complexity for the solution. And it also makes the problem convex. So actually, that leads me right into the next slide, which is how do we do this allocation per frame? Well, we're going to introduce a time-expanded network graph, a data structure which we call the network flow interaction chart. I talked about earlier, the interaction of frames in space and time. And this might be something that you've seen before, but I'll illustrate it using this small example of 4 terminals, A, X, Y, and B. The way we construct the graph is we take the terminals of the network and we make them nodes along the y-axis of our charts. There's A, X, Y, and B. Then we represent time on the x-axis. So each one of these replications indicates one time slot. You then can draw edges between the nodes in this graph to represent transmission. So edges coming out of terminal A here indicate that there might be a wireless transmission between A and X, A and Y, and A and B, or A and B, for instance. Now notice that I've also drawn an edge from A to itself in a time slot. That just corresponds to the data being stored in memory. So you can think of a terminal transmitting to itself. That's just, it saves its data for one time slot. So this graph is kind of represents what could happen in the network. Now we need to somehow bring in the topology. We're going to do that by assigning edge weights to each of these edges, corresponding to the rate that such a link can sustain. So here, each of these edges is going to be weighted according to log 1 plus SINR. So that's the link capacity. Now, at the beginning of time, before we've allocated any resources for anything, each of these links is actually weighted with log 1 plus SNR because there is no interference. Before we've solved any subproblem, there is no terminal in the network. So the denominator is just the noise. And we've assumed that there's some maximum transmission power, which specifies how loudly a terminal can transmit. And we use that value to calculate this log SNR. So now how do we use this graph to allocate resources for a frame? Well, I'll walk through a small example in this little network. Suppose we want to allocate resources for one frame, from terminal A to terminal B. The first step is we weight the source node with infinity here. So this indicates that we're trying to send as much data as possible, some large amount of data from A to B. And all the other terminals, because we're allocating resources for only one frame, all the other terminals are assigned weight 0. What we do now is basically execute a dynamic programming procedure that's quite similar to shortest path routing, where we update each of the edge weights with the minimum of their initialization weight and the node weight. So the idea here is that a wireless transmission can only handle either as many bits as the channel will support, that's what Shannon says, or practically as many bits as there are at the source terminal, which is why we take this minimum. Then at each of the nodes, so that this is the edge update, at each of the nodes, we update with the maximum of all of the incoming edges. And the idea here is we want to receive as many bits as we can. We're trying to maximize the amount of data we can put through this network. So after the first time slot, I'm going to look for as many bits as I can possibly get from terminal A. And in this case, it's always going to be the direct link because we only have one time slot to work with. So this procedure iterates. We do minimize the edge weights, take the maximum of the incoming edges, and we keep doing this until all of these node weights have stabilized. Stop changing over time. Yes?
I think I missed the explanation why the edges are updated with the minimum of nodes and what does it mean anyway? The minimum of edges and nodes?
So, okay, so each of these nodes has a weight. So that was assigned at the very beginning. We said, all right, we're trying to allocate resources from terminal A. So we assign each of the nodes at the very beginning of the graphs, index 1.
And that
with
weight represents what?
That weight represents the number of bits that we're trying to transmit. Okay. Yeah. So that weight here, because we want to send as much as we can, is infinity. And then the edge weights were actually weighted with log 1 plus SINR. So the edges represent the transmission. So that weight is also in bits. How many bits can the transmission support? So then what we do here is we update with the minimum, we update the edge weight with the minimum of what it was before, which was how many bits it can support, and minimum of that and the node weight, which is how many bits are at the source.
Note that they on the left or on the right.
So on the left, yeah. So it's iterating to the right. Yeah, that's an important point. It's directed to the right. And then with the edge weights, we update with the maximum of all the incoming arrows. So we can think of it as happening first in time slot 1, then 2, then 3, and so on. And then at some point, the node weights stop changing. And you can show that once they've stopped changing, you've identified the data maximizing paths from the source, in this case terminal A, to every other terminal in the network. So what we're trying to do is maximize throughput. So what we do is we look at our destination, which in this case is terminal B, and the weight at terminal B in each of these time slots is going to be representing the maximum number of bits that a route of, in this case, 1 time slot, 2 time slots, 3 time slots can support. So in the case of a 1-hop route, it is just the direct link. That's always going to be what that represents. 2-hop route has some intermediate terminal, but might offer more bits. So in order to compute the throughput, we divide the value here at the destination node by the number of time slots that we've needed to allocate that route. Suppose that it's the 2-hop route that maximizes this. In this case, maybe it's from A to X, and then from X to B. If we have to identify this as the maximum, we track back through the chart to figure out what path got us there. And this gives us both our schedule and our route. So in this case, first time slot, A transmits to X. Second time slot, X transmits to B. And this is an allocation for 1 frame. That's just 1 frame. So what we can do with this chart and that algorithm is we can enforce the routing constraint. So that continuity of route is naturally enforced. So are the broadcast and multiple access, because we can only allocate 1 arrow at a time. What we're going to do is set the rate for every terminal in the path according to the bottleneck. So in this network, with this very small example, the link from A to X is going to be our bottleneck because it's the longest one, largest geographical distance. So what we'll do for the second time slot is turn the power at terminal X down. We'll reduce that such that this rate is the same as this rate. So all of the links operate at the same rate. Now this reduces interference and also conserves power. Yes?
Do you allow flow splitting?
Not in this formulation. We'll talk a little bit later. When you allocate more than 1 frame per flow, that is kind of what happens. But when we're allocating just 1 frame at a time, we don't do it. And we can show that per frame, this dynamic programming procedure does return the optimal allocation given resource availability. And unfortunately, we can't say anything about the optimality of the overall solution because it's NP hard. But per frame, we are getting the optimal answer. So after we've allocated resources for 1 frame, now we have to go back and make them unavailable for anybody else. So how do we do that? Well, if this was the allocation that we had for A to B, in the first time slot, terminal A is transmitting, so it can't receive, which means that the half duplex constraint binds there. So any arrow into terminal A has to be removed from the graph because it can't receive in that first time slot. And the same thing is true of X in the second time slot. Now we enforce the broadcast constraint. A can't transmit anywhere else or remove its arrows. Multiple access constraint. X can't receive from anyone else in the first time slot, so we remove those arrows. And now we're left with a pretty bare graph in this case because this network is so small and we're using up almost all of the resources. If we were trying to allocate another frame in this little network, say 1 from B to X, it might have to take a route something like this. In the first time slot, B transmits to Y, stores its data through the second time slot, and then transmits on to X in the third time slot. That's just because we have such a small network. But now notice something interesting has happened. We allocated resources for the black frame, and then we came back and allocated resources for the blue frame, and the solution turned out to include that interference model that we talked about before. We now have 2 active links at the same time. We need to make sure that when terminal B transmits, it's not going to interfere too much with the transmission from A to X, because we've already allocated that one. So now we have to couple these transmissions through the interference. Yes?
So I'm trying to understand why you take into account this multiple access constraint, because you are considering that there can be 2 simultaneous transmissions. So B is transmitting to Y, and even though A is transmitting to X, it can somehow find that out and discard that. So in the same way, if B was transmitting to X,
B is sending to X.
if
Yeah.
yeah, at the same time as A is sending to X, can that happen? Because you're saying multiple links can, multiple transmissions can occur,
Yes.
but not at the same node.
But not the same terminal can't receive more than one at a time. We've assumed that our terminals are relatively simple, so they don't do successive interference cancellation or anything like that. If they could, then they could receive more than one frame at a time. Does that make sense? I'll talk a little bit later about what happens if you have terminals that are full duplex, transmit and receive at the same time. But I think you make a good point. If we were to permit that, then, or some kind of multiple access scheme, what that would mean in this graph is that those edges remain, but the weights update to reflect how much successive interference cancellation terminal X could do, for instance. For now, we're assuming none, so the edge goes away. But you could incorporate that into our model. That's true. Okay, so what we need to do is manage these simultaneous transmissions. We allocated the black flow first. Now we need to make sure that the blue flow doesn't interfere too much. So how do we do that? Well, we have to have some way of guaranteeing that previously allocated frames, so in this case the black one, is not going to be affected too much by subsequently allocated frames. Remember, we're solving this sequence of subproblems. Once we've computed the solution to a subproblem, we can't harm it too much with the solution to another one. So we need to update the edge weights in our graph, which represents or means that we change the maximum transmission power in the network in a given time slot. So we define a parameter. There's a knob in our model that we call the allowable interference, or R sub int. So if we've allocated this black frame and say its rate is R, for instance, or RA, then we're not going to permit any subsequent allocation to reduce that rate by more than a fraction R int, and this is a value between 0 and 1. If R int is 0, then we don't affect the rate of a previously allocated transmission at all, which means that we basically reduce to TDMA. That precludes any other simultaneous transmission. If we let R int be 1, then we don't care about any previous solution, and we stomp all over previously allocated frames. So this is a value that we tune. In our case, we haven't found a good way to actually solve for it in an optimal sense. But through simulation, we've shown the value of about 0.3 seems to yield the best solution. And why that is something we're still looking at. But what that means is we say, okay, we know that this link operates at, say, 10 bits per second. We're not going to allow it to drop by more than 2 bits per second. So if we allow this link to drop down to 8, what's the maximum power that any other terminal could use? Well, in the case of terminal B here, terminal B is quite close to the receiver. So terminal B is going to have to turn down its transmission power a lot in that time slot. Whereas terminal A here in the second time slot, because it's so far away from B, which is receiving, isn't going to have as much effect. So we update these edges. We say, all right, first time slot, terminal B has to really quiet down in order to reduce, to not interfere too much with the black flow. Terminal A can still have a pretty good transmission shot in the first time slot, or second time slot rather, because it's not going to interfere as much. So this is kind of a cartoon view of what happens in the algorithm. But what it really means is that the frame rate has been set by the bottleneck. And by changing these maximum transmission powers, the bottleneck in one part of the allocation, in this case A to X, is going to affect the interference profile in another part, because these routes are all coupled geographically. This is all a consequence of our path loss model. If you change the channel model, everything looks very different. But for now, because we're just considering path loss, we have this nice coupling. So this is the high-level view of what we do. Let's look at it in an example and see how things work. So here's a case where we have 3 flows. We have blue to blue, which will be allocated first because it's the longest. We have red to red allocated second, and green to green allocated third. We just click on the route that gets established. This is the sequence of terminals that each of these frames is going to pass through. Now if I click through each time slot and show what's happening at each time slot, in the first time slot, the network, everybody's using it. We're all sharing. This is the sharing part. Time slot 2, we're still all sharing. Time slot 3, now notice that red and green have to cross each other. In time slot 3, we switch into that TDMA mode, where the green packet, or green frame, is held at this terminal in the memory. That's that flat line through the graph, while the red frame passes by. So the red frame now comes in this 5th time slot. Blue comes in, and then green comes in. So 2 things to note here. First is that the red frame has been routed to the left to avoid the blue frame. This is the notion of sharing. This is, we can both use the network at the same time if we don't get too close to each other. So the red frame would be routed more directly if there was no other need for the network resources. It would, if it was the only flow, it would be routed more directly to its destination. But because the blue frame is also there, we can share the medium by routing them around each other in some sense. And in this case, also, we had that notion of the shouting, where the green frame waited for the red frame to pass. So green deferred, that's where red shouts right through. And the red route indirectly avoids the blue one. And that's the notion of sharing. Yes?
So you assume a buffer as each node, right?
Assume what? Sorry.
A buffer, there's a buffer.
There's a buffer, yes. Yeah. Of some size. Right now, we've assumed that it's infinite. But if you want to make it smaller than that, what that means in our graph is that that flat line has a weight corresponding to the buffer size in bits.
But for each flow, every node on that flow, I mean on that route, the buffer size is the same, right?
It's the same.
Frame size.
Right, it's all the same. That's something you can tweak, but for now we assume it's all, everybody has infinite storage. Yeah. Okay, so this is an allocation for just one frame at a time. And what we could do is, after computing this allocation, repeat it over and over again to send streams of packets. But let's look at another example where we actually take advantage of spatial separation to, I think this is what we were hearing about earlier about flow splitting, where we allocate frames that go in different places. So here we're going to allocate resources still for 2 flows. It's the same 2 from the first example, but 2 frames each instead of just 1, 2. And the sequence of subproblems is going to be red, one frame for red, 1 frame for blue, then another frame for red, and then another frame for blue. So this is that heuristic from before. We're trying to maximize minimum throughput, do the longest, then the shorter one. So the solution turns out to look something like this. We share in time slot 1, time slot 2. Now notice the red source is sending out its second packet. Time slot 3, the first red packet comes in. Time slot 4, the second red packet comes in. So we've avoided that half duplex penalty there by using 2 different routes through the network. If we click through, the blue guys have gone around or let the red ones pass. Time slot 5, 6, everybody's in. So what we notice here is that by splitting the frames up in space and using other terminals, we can avoid that half duplexing penalty. And that's just through utilizing geography. And what you can do with this is you can extend it and have many, many more frames. One of the interesting results that we found is that for networks of this size, where we have roughly 40 terminals and between 2 and 4 flows, there are about 5 distinct routes that packets take in a streaming allocation of about 100 frames. So 5 seems to be enough to get everybody through without too much self-interference. Because in here, when we had, say, these 2 packets on the network at the same time, they were interfering with each other. So that also has to come in. Okay, so one of the things that I haven't talked about very much is how do you determine that value of reliable interference? As I said before, if it's 0, if you don't allow anybody to interfere after they've been allocated, then you'll get a totally TDMA system. If it's 1, you have full interference, and you don't care about solutions to previous problems, which is probably bad. How do we determine it? For now, we've been using a simulation approach, but there might be a smarter way to do it. As I said, it's still an open question. One idea we have is kind of an iterative refinement technique, where after you've allocated resources for some packets, you look at the allocation and you see how much interference is happening. You might tweak that R-int. We're not sure exactly how this technique would look. Another way would be to maybe consider a pricing model. If you know something about the flows, if you know that certain packets have higher priority than others and need to be protected more, then you can change this R-int on the fly, depending on what packet's being allocated. And then lastly, we're thinking maybe topological dependence. If you know that you have clusters of terminals that have some property that maybe there's a base station there that can handle interference better, you might be able to adapt R-int accordingly. And then any ideas would be appreciated, because this is still an open question. One last thing I'd like to look at or mention to you just before I finish up is some new ideas that we've had on using this framework to look at resource allocation when terminals are permitted full duplex behavior. So at Rice, we've just recently brought online a demo of 2 radio nodes on Warp Hardware that actually can transmit and receive simultaneously. And this has shown great gains for single flows. If you have just point-to-point links that are bidirectional, full duplex has been really a real help. But what are the large network implications? Because as soon as you have more transmissions, you also have more interference. So this interference needs to be managed. We're going to use our network flow interaction chart to look at multi-flow allocation where full duplex is allowed. We're going to try to understand what are the topologies where full duplex is helpful, and do all terminals need to be capable of full duplex? Because at least in our setup,
So here by full duplex, you mean they're on the same frequency?
same frequency, same time slot, yeah. And the way we do it is we have two RF chains, one for transmit and one for receive, and then a third RF chain, which is transmitting a cancellation signal to ourselves. So we cancel out our own transmission at RF, which is why it's kind of expensive when you have three RF chains. So do all of the terminals need to be full duplex?
So how is this different from the paper that the guys at Stanford wrote?
I'm not actually familiar. I'm not sure exactly how they did it in hardware.
Yeah, I don't believe they had three RF chains.
Okay, did they do like passive cancellation? They just
I
added
don't remember the details, but there was, I recall sort of.
Okay, I'd have to ask my.
I don't
They
know.
also had some kind of cancellation. They had
They have
three
third
antennas.
RF chains? Oh, okay, so they have the same thing.
So they
Okay.
had pretty much.
My office mate is the one who really did the heavy lifting on this project. I could ask
That's like the
her.
entire slide on the comparison between the two.
Yeah.
Oh, okay, so therefore,
I don't
okay, so they also use the third RF chain?
Yeah.
They do? Okay. Now, so there's something special about doing RF mixing or signal mixing at RF that is somehow a critical component of doing it right.
So how robust is this?
Yes, yeah, they showed very limited cases, right? I think Ivan knows about the full duplex field of
Oh, Stanford,
yeah.
Stanford, yeah.
So how robust is it? That's the question.
Yeah.
Good luck.
Very limited cases, right? Like,
Yeah, ours
I don't
is.
even know if it really works.
So that's a big question, right? So filmmaking independent confirmation.
So these guys said they have a demo of
Yeah, Rice. What?
warp terminals.
Yeah,
So
two-way channel?
it's a two. Yeah,
is it full duplex?
it's full duplex.
But
Yeah.
so what's the antenna separation?
It's actually, I think she looked at 10, 20, and 40 centimeters, and she found that 20 was sufficient. I can talk about it a little bit more. Let me maybe just finish this up, and then we
Yeah,
can
go.
discuss. Yeah, I just have 2 slides, and then I'm done. So we're trying to look at the medium access issues of this, and using our framework, it's very easy to see that a simple modification, just drop that half duplex constraint, means that now if terminal A is transmitting in the first time slot, it can also receive. So those edges remain in the graph. Where the weight on them, so the links could be bidirectional. Now X can transmit to A while A transmits to X. But the weight on them depends on the cancellation technique and other interference in the network. And it's this thing right here, this cancellation technique, that we can talk about in just a second. But let me give you a small demo or simulated demo of where this can be useful in a large network allocation. Let's suppose we have a single frame for 3 flows, so the same thing we were looking at before. What is full duplex bias? Well, in this allocation, in the first time slot, it's working here because these guys are sharing the medium and that blue terminal is receiving and transmitting together. And in the second time slot, it's happening in 2 places. The green frame is being received while this terminal is transmitting the blue frame, and the same thing's going on over here. In the third time slot, we're back to just half duplex operation, and everything gets through to its destination. So full duplex is reducing frame transit times, and in doing so, even in cases where there are not bidirectional flows, these are both unidirectional, or all 3 are unidirectional, but full duplex has afforded us some gains. Another thing to point out is that only 3 of the 7 terminals that are active in this network are using full duplex, so we didn't need it everywhere. We just used it where there was interaction from frames of different flows. That's where it was helpful. So going forward, we'd like to look at some protocols for establishing full duplex behavior. This is something that I think is quite an open area. And also trading off the power required for full duplex, using that third RF cancellation path, versus the complexity required implementing it on a device, versus the improvement that it offers in throughput. So it's giving you gains in throughput, but it's costing you in power and complexity. How do these things trade off? Is full duplex really going to be worthwhile in the grand scheme? And as I said, this is something that I've only been looking at in my framework for the last 10 or 15 days, very recent, but that the people at Rice have been looking at on hardware for quite a bit longer. So just to wrap up, in summary, I've shown a general framework for large-scale resource allocation that trades off interference and scheduling according to that Rn parameter, and we have optimal solutions up to a frame. Given network conditions, we optimally allocate 1 frame in polynomial time. The whole solution, the combined solution, we can't say anything about the optimality of that just because of the nature of the program. But going forward, we're going to ask ourselves, is the decomposition technique that we use really the right one to do? We're using that heuristic of longest path, then second longest, and so on. Is that the smartest way to do it? It's not clear that it is. Then, as I mentioned before, tuning that interference parameter. And iterative techniques for updating our solution. After we've allocated the first frame, maybe we allocate 4 or 5 more, then we go back and we see if that allocation for the first frame was optimal, or not optimal, but was maybe should be updated in some way, based on what other resources are required. And more recently, we've been looking at protocol design. I've assumed that I know everything in the network, and when you see that network graph, I needed all n-squared channels, which is just ridiculous from any kind of an implementation perspective. Are there ways to distribute this technique? And then lastly, some applications of it. So I mentioned the full duplex case, but we can also use our technique to look at when should cooperative terminals be introduced into a network, because that's interference too, but it's scheduled interference. It's good for some flows and bad for others. When can we employ cooperation? And we've also just started up looking at video over large networks. When you have knowledge of the priority of different frames, you know that some frames need to get through, otherwise they'll cause a lot of distortion, whereas other frames you might be able to drop. How do you allocate resources under that paradigm? That's something that we just started looking at. So that's about all I have. So thank you very much.